Hello everyone, welcome back. Today we are going to discuss another important part of IBDP analysis and approaches HL Maths syllabus, that is Maclaurin series. So Maclaurin series is basically a power series whose center is at 0. Considering the syllabus last change in the syllabus, you don't really need to know much about power series or center of a series. So you can think of a Maclaurin series as a polynomial. Polynomials like cubic polynomial or quadratic polynomial, linear polynomial. Similar to this, Maclaurin series is just a polynomial that never ends. So it is an infinite series where powers of x are integer values. If you write a general Maclaurin series, this is how it looks. A0 plus a1x plus a2x squared and so on and so forth, where a0, a1, a2, a3, these are coefficients of Maclaurin series, and each of these are real numbers. Now, an example of this could be this infinite series 1 plus x squared plus x cubed and so on and so forth. So this is a Maclaurin series. Now, we also know that this is a simple geometric series whose first term is 1 and the common ratio is x. So if absolute value of x is less than 1, or when the value of x lies between negative and 1 and positive 1, this series will be a convergent series. And if it is a convergent series, we can find sum to infinity of this series, and that is going to be u1 over 1 minus r, that is first term divided by 1 minus the common ratio. So sum of this series will be 1 over 1 minus x, and obviously 1 over 1 minus x is a function where x is not equal to 0. So a convergent Maclaurin series, in fact all Maclaurin series which are convergent, can be expressed as a function. So the question is, if we can express a Maclaurin series as a function, can we express a function as a Maclaurin series? And your answer is yes. So to express a function as a Maclaurin series, what do? We use our basic understanding of calculus. How does this happen? Have a look here. So let's say this is a general Maclaurin series, a0 plus a1x plus a2x squared and so on and so forth. If you write the derivatives of this series, then the first derivative a0 will disappear because there is no variable here, and then the first derivative of this series will be a1 plus 2a2x 3x squared and so on and so forth. If you differentiate it again, the second derivative will be this, the third derivative will be this, and so on and so forth. Now, out here, if you find the value of the function and value of derivatives of this function at x is equal to 0, what do we get? For example, out here, f naught will be, see all these terms have x values except the first term, so f naught will become a0. Similarly, f prime 0 means the first derivative at x is equal to 0 will become a1. Similarly, second derivative at x is equal to 0 is 2a2, and the third derivative at x is equal to 0 will be 6 times a3. We would like to see a pattern here, but we don't have any pattern. So one of the ways to identify pattern is one of your problem solving skills. So what we can do is, we can break these coefficients. So if you see a1, can we write a1 as 1 times a1? 2a2, can we write 1 times 2 times a2? 6a3 will become 1 times 2 times 3 times a3, and also a0 we can write as 1 times a0. So if you see 1, 2, 3, this is factorial 3. 1 times 2 is factorial 2. 1 is factorial 1, and 1 is also factorial 0. So if we rewrite these derivatives in terms of factorial notation, this will be 3 factorial times a3, 2 factorial times a2, 1 factorial times a1, and 0 factorial times a0. Using this, you can see value of a naught will be value of function divided by 0 factorial. First derivative at 0 will be, a1 will be first derivative at x is equal to 0 divided by 1 factorial. A2 will be second derivative divided by 2 factorial. A3 will be third derivative divided by 3 factorial. So A9 will be ninth derivative at x is equal to 0 divided by 9 factorial, right? So we have identified a pattern. So we will use these values and let's rewrite this general Maclaurin series. So a naught will become f0 over 0 factorial. First derivative at 0 over 1 factorial will be your a1, and so on and so forth. So this is another form of this Maclaurin series, and we will use this form of Maclaurin series to find the Maclaurin series corresponding to different types of functions. Let's explore this with the help of a function. Let's say y is equal to fx, or fx is equal to e raised to the power of x is a function. This is general Maclaurin series we just derived. So if you find the first derivative of function, this will be e raised to the power of x. It remains same. Even second derivative, third derivative, they all will be same. Find the values of these function and these derivatives at x is equal to 0. So you get e raised to the power of 0 is 1. So all these will be 1, 1, 1, 1, 1. Now plug in these values up here. So these values, when you put into this formula, what do you get? You get e raised to the power of x is equal to 1 plus x squared over 2 factorial plus, and so on and so forth. So this is the Maclaurin series corresponding to e raised to the power of x. This is how we write. So what do? We find the value of function at x is equal to 0, first derivative at x is equal to 0, the second derivative at x is equal to 0, the third derivative at x is equal to 0, and so on and so forth, and just plug into this form. Let's do it. Let's revisit it with the help of another example. Let's say this time your function is a trigonometric function, sine x. So we write fx is equal to sine x, first derivative of sine is cos. So cos x, then negative sine x, then plus negative cos x. Now when you find the value at x is equal to 0, all signs will disappear. So to get the first 3 or 4 terms, you need to have more derivatives. So we differentiate again, fourth derivative is here, fifth derivative is here, and so on. So value of a function at x is equal to 0 is sine 0, which is 0. So it becomes 0. Then you have 1, negative 0, negative 1. This is again 0, and this is positive 1. Same thing, again we plug in these values in this Maclaurin series general equation. So f0 is 0, first derivative is 1, so 1x, then second derivative is 0, so it's gone, third derivative is negative 1. So you see alternately you get positive negative terms, and also you get only odd powers of x. So out here you will get x minus x cube over 3 factorial plus x5 over 5 factorial, and so on and so forth. So this is the Maclaurin series for sine x. This is Maclaurin series for e raised to the power of x. You will be given these in your data booklet, but I suggest you should understand how these are derived. It will help you to solve exam questions at the later stage. Now, not all functions are very friendly to differentiate. Sometimes when you find first, second, third derivative, they become more and more complicated. So what do? We again use our concept of calculus. So if you differentiate a function, you get a function. gradient function, and if you integrate that gradient function, you're back to your main function. So we will use this concept to approach in finding Maclaurin series for functions in a different way. How we look at this function? Arc tan x, that is tan inverse x. In IB terminology, they use arc tan. So we may switch between arc tan and tan inverse. So if this is your function, if you differentiate arc tan, then the first derivative is 1 over 1 plus x squared. And if you remember, we just did this series 1 plus x squared and so on. This was 1 over 1 minus x. When x becomes negative x, you get 1 over 1 plus x is equal to 1 minus x plus x squared minus x cubed and so on and so forth. When x becomes x squared, what do you get? 1 minus x squared plus x4 and so on and so forth. So this 1 over 1 plus x squared, if you replace by 1 minus x squared plus x4 minus x6 and so on, this is how it looks. Now remember, this is derivative of fx. This is gradient function. So how to get back to the function? We just integrate. That's all. So when you integrate, 1 becomes x squared becomes x cubed by 3, x5 over 5. So integration of this will be function fx, which is tan inverse or arc tan x. So the Maclaurin series for tan inverse x will be x minus x cube over 3 plus x5 over 5 and so on and so forth. So this is another approach. Even for log function, we can use this approach. So I suggest find questions and see which approach works well and why does it work well. To get better and better in this topic, the only way is to practice. Once you practice, you will get better. And another suggestion would be, please memorize your formulae. Memorize them. If you know formulae, you can think 2-3 steps ahead. And if you always refer to your data booklet, formula booklet, you'll be slow in exam. And what you need in exam is sharpness and pace. So it's really important to memorize these formulae. So if you found this video useful, please like it, subscribe it, and press the bell icon to get notification of new videos. Share it. You can also reach to me at jalajmaths@gmail.com or at Instagram jalajmaths. And till we meet with a new topic, take very good care. Bye-bye.